Hi, everyone. I'm Guilherme Xavier from the Electrical Engineering Department at Linköping University in Sweden, and I'm here to present our work called Minimizing Detection Losses from Time-Being Quantum Cryptography Systems with Field Mode Fiber Technology at QCrypt 2021. I would also like to thank the organizers for being able to pull off this conference in online mode, because it has been a very difficult couple of years, and we hope that maybe next year the whole situation will be better. So now, first, I would like to go over some basic concepts that will be helpful throughout the presentation. So typically, if you have your quantum state that you would like to transmit over, for example, a quantum communication protocol such as quantum key distribution, you need to encode it into a degree of freedom of a single photon. And there are several ways to do so. So, for example, these are four very popular forms of encoding. So you have polarization encoding and path encoding, which now is gaining a lot of prominence because of integrated photonic circuits. Then you also have time-bin encoding, which is one of the main points of this talk, which and this is it has been very popular over many years, because it's a very convenient form of encoding if you want to do long distance transmission over optical fibers. More recently, another technique that has been gaining lots of traction, so especially in free space, but more recently also over optical fibers, is orbital angular momentum encoding. And if you want to move to high-dimensional quantum systems, which there is a lot of motivation to do so. So, for example, you might want to achieve faster transmission rates, or there are some protocols that can only be achieved if you work with high-dimensional quantum systems. Then you, of course, have to drop polarization encoding, but all the other three are good candidates for high-dimensional quantum information, and they have been applied over the last few years. So this paper will actually deal with a mixture of these types of these three different types of encoding. The other aspect that I want to briefly discuss is spatial division multiplexing, because it's actually the technology regarding fibers and components that we are using to be able to do this kind of experiments relies on SDM. So this is the most recent technology that has been deployed to boost the transmission capacity of optical networks. So there have been a number of different technological advancements over the years to basically be able to boost the transmission capacity of the internet. And this is only growing with time. SDM is basically the most recent development in that aspect to be able to keep the growth of the internet as it has happened over the last decades. So spatial division multiplexing is basically a new novel optical fibers that supports more than one transverse spatial propagation mode. And you also have the appropriate components like multiplexers that basically can join several different single mode signals onto the same optical fiber. So we are going to be discussing photonic lanterns, which is the spatial multiplexer that we use. And the reason why this was developed for the telecom industry is to basically be able to multiplex a number of different channels containing different signals, or basically different data, into the same optical fiber. And so a number of groups, including us, have been actually doing experiments recently using these types of fibers for quantum information. So multi-core fibers have specifically been already shown within several experiments, as well as field mode fibers. But we, to the best of our knowledge, this is the first experiment that's using lanterns to excite and detect modes containing quantum information over these fibers. ring core fibers have also been popular for orbital angular momentum very recently. And we also have few mode multi-core fibers, but this, as far as I know, there have not been any experiment employing this for quantum information applications yet. We also need to briefly discuss the photonic lantern, because this is the key component of our work. So as I said, it basically takes a number of, in our case, 3 single mode inputs. So basically 3 separate paths, and it will multiplex them onto the same optical fiber, where each path will excite a separate mode a separate spatial mode onto the field mode fiber. And the typical structure of what it looks like, it's basically 3 fibers that are slightly different. So they have slightly different radii, but they are still all single mode for telecom wavelengths. They are basically adiabatically tapered. So basically that means you employ a long and slow taper all the way down to a field mode fiber, and this is all encapsulated into a specific capillary to basically be able to hold a cladding when the 2 fibers are fused together, so that, I mean, you don't have an air, so that you don't have air as your cladding all the way down here. So the component we employed is commercial, so it can be bought. And this is, for example, from this quite famous paper, where you can clearly see the different modes when you connect inputs to the different input fibers. So you get the LP01, which is the fundamental Gaussian mode, and then the 2 higher order LP11A and LP11B modes. And this type of lantern is called a mode selective lantern, because if you input your signal onto a single input, you will only excite the appropriate mode. So now let's briefly discuss phase and time bin QKD. So this is the original proposal of phase encoded QKD. And basically it's simply a long distance Mach-Zehnder interferometer, where Alice has a single photon source, which is then split by a beam splitter or a fiber coupler into 2 parallel paths. And then in one of them, Alice has a phase modulator to be able to change the relative phase between the 2 paths. And this gets transmitted over 2 separate single mode fibers. And then Bob will have a similar phase modulator to be able to perform his measurement selection. And then the 2 modes are superposed into another fiber coupler, and the 2 outputs are projected, are read by 2 single photon detectors. And both modes will arrive together at the same time, so they will superpose in time, and then you get interference between these 2 modes. So the phase encoded qubit in this case looks like this, or this is also a path encoded qubit. And the output probabilities are, of course, in this case, simply proportional to cosine square and sine square, depending on which detector you are looking at. So they are complementary. And this kind of setup can be readily used to implement BP84, for example. The main drawback is that you need a long interferometer if the transmission distance is significant. I mean, unless you're doing this experiment on the optical table, you're going to have a long interferometer, which is cumbersome to stabilize, although it can be done. But it's something that it never really picked up over the years. In the same paper where the phase encoding proposal was done by Bennett, he also proposed time bin encoding to solve the problem of the previous configuration. So actually, instead of having 2 parallel paths connecting Alice and Bob, he proposed the use of unbalanced Mach-Zehnder interferometers, such that you convert from these 2 parallel traveling modes to 2 serial modes, one going after the other, so that then you could have a single fiber. And this has been then later called the time bin configuration. So you typically have an early and a late path, which are then recombined with another fiber coupler. So this is an asymmetric Mach-Zehnder interferometer, and you have a phase modulator placed into one of the arms, which can basically switch the relative phase between the 2 pulses. So this is what Alice's setup looks like. And then you have a time bin encoded qubit, which looks like this. So you have a coherent superposition between an early and a late timebin, and this gets transmitted over a single optical fiber. And this is what the complete configuration looks like. So you have the single fiber link connecting Alice and Bob has an identical unbalanced maximum interferometer, but now he also has another phase modulator, which allows him to basically choose the measurement basis as well. And of course, Alice's phase modulator is used to choose the state which will be transmitted. And then all the different modes will superpose again onto the final fiber coupler. So basically, this is also it also works as a Mach standard interferometer, but with the difference that not all the different post combinations, or meaning the different timebin combinations, will arrive together in time in this final fiber coupler. So for example, because you have 4 different possibilities of paths that the photons can take. So they can either take the early, late, or the cross early, late, early combinations. But of course, the early, and late, they will be distinguishable in time, so they do not interfere. And of course, again, as I said, only one fiber is needed, which is much easier to actively stabilize 2 shorter interferometers than a long one. So this configuration has been extremely popular over many years. And the one thing that in order to be able to have a high visibility interference pattern, meaning that you can extract a secret key, is that you have to post-select the 2 timebins that don't interfere, because otherwise they will be just read as noise as random detections in your setup. So basically that will incur a 50% loss in the detection stage. And the loss will, of course, increase for high dimensional systems, because then you have more combinations that you need to get rid of. And for example, in the case of D = 4, you only keep the central peak, while you have to discard all the other ones. And it's only in this case where you have, meaning that you actually have a 75% loss in your system. And if you go over even higher dimensions, so in the general case of D dimensional qubits, the loss is D-1/D. So this problem, of course, becomes more prominent as the dimensionality increases. And now to discuss our proposal and the results we've obtained. So we actually proposed the combination of both phase encoding and timebin setups in kind of by exploiting few mode fibers. So the basic idea is that we still kept the 2 short interferometers at Alice and Bob, but now they're no longer unbalanced, because each of the path modes is actually assigned to a separate mode through the photonic lantern onto the few mode fiber. So you still get a single fiber for transmission, like the timebin, but you only have 2. You don't have no longer the asymmetry, and you no longer have the time separation between the timebins, or in this case, between the 2 spatial modes. So this gets transmitted, and you have another photonic lantern to demultiplex the different modes onto the appropriate paths. Once again, Alice and Bob have their phase modulators, and this will basically be superposed again on a fiber coupler, but they are also superposed in time, which means that you no longer need the post selection. So again, you have the phase encoded qubit here on the input. And once again, the outputs are proportional to cosine and sine squared at D1 and D2, depending only on the difference between the phases of Alice and Bob. And now we are no longer required to have post selection. And like just similar to the timebin setup, as I said, only one fiber is used. So of course, this is all very nice, but we need to see that we can actually generate the appropriate states. So inside the fiber, the qubit is actually a coherent superposition of the different LP modes. In this case, we're using the LP11A and LP11B modes of the fiber, and they have the advantage that they propagate with the same velocity. So there is no modal dispersion affecting them. If we had used the Gaussian mode, then that would be one consequence as well. So the way we characterize the spatial states is by using an InGaAs infrared CCD camera. So, and we worked with our laser. So it's a telecom semiconductor laser. So we're working in the 1550 nanometer telecom window. And we basically created our states using this phase modulator over the two paths. And then we joined the paths on mapping them to the LP11A and LP11B modes over the field mode fiber using a photonic lantern. So we use imaging optics to image the output facet of the fiber onto the CCD camera. And we did this in the back-to-back configuration, meaning that so we just connected the output of the lantern directly to our imaging system and to the CCD camera, and then we then inserted a field mode fiber spool of 500 meters. It's a 3-mode fiber from OFS, and we then imaged the states after the propagation through the field mode fiber to be able to observe the evolution of the states. And we are interested in as an example, to basically be able to observe the states generated by, that are useful for BB84 QKD. So basically, we are using the typical, the typical BB84 states where the phase difference in analysis qubit is 0 and pi for one mutually unbiased basis, and pi over 2 and 3 pi over 2 for the other mutually unbiased basis. And interestingly, this combination allows us to generate the OAM modes plus and minus 1. So basically, this is I'm going to comment this in the end, but it's a way to generate and detect OAM modes using only fiber means. And these are the experimental results. So these are the theoretical model distributions, and these are the experimental results. We've also included the pure LP11A and LP11B modes. And you can, the most remarkable thing is that there is no significant difference in quality of the modes between the back-to-back and 500-meter propagation cases. So this actually shows that probably there is significant potential for longer transmission distances as well. So this is something we would like to see. And then we replaced, so we actually increased attenuation on the laser to basically be able to enter the single photon regime. And we replaced the camera with Bob's detection system. So basically the other photonic lantern and decoupling the different modes, the phase modulator, and then the fiber coupler closing the interferometer. So these are the single photon interference fringes by continuously modulating Alice's phase modulator while fixing Bob's. And these are, from this data, we've also simulated the BB84 protocol by basically measuring the different states versus the different projections. And the average probability of the main diagonal is over 95%. And for 0 and 500 meters. And again, as a consequence of the fact that the mode did not distort too much, you can see that there isn't significant difference in the probabilities after propagation over 500 meters. The main limitation for these numbers we attribute to the extinction ratio of our photonic lanterns. They are commercial components, but they have an extinction ratio which is around 16 dB at the best case. So it's one limitation that we have right now. And finally, we also wanted to show that field mode fibers, they offer high stability of the relative phase between different spatial modes going over the fiber. So this was an idea that we wanted to check, because if one motivation for the use of field mode fibers over, for example, multi-core fibers, is that all the modes, they travel through the same core. So we speculated that there shouldn't be much phase drift between the different modes while they're propagating in the fiber, while over multi-core fibers, there is some residual phase drift. And we actually showed this by basically doing a 1 hour long measurements over 1 hour of, so we went back to the classical intensities, and we replaced the single photon detector with a PIN photodiode, and we continuously modulated with 100 Hertz Alice's phase modulator, and we didn't do anything with Bob. So we would expect that there would be a difference between the back-to-back, from the back-to-back to the 500-meter cases, from the environmental phase drift, which should actually add lower frequency components, because neither Alice nor Bob's interferometers were actively phase stabilized. So they were only in the lab with a thermal enclosure, but there are drifts over time. But the key point is that there is no difference in, so this is the FFT of the time signal over the back-to-back and the 500-meter cases. So basically, this means that the fiber is not adding extra phase drifts because of its length, as it would be expected, as it happens for a multi-core fiber, and of course, as it happens very, very rapidly for pairs of single mode fibers. So this is something that it gives, I mean, more promise to these fibers for this type of experiments. So where to go from here? So very quickly, one idea is to, of course, expand the experiment to higher dimensions. Our fibers and components already support 3 modes, so we could, that's one thing we are looking to try. And but of course, if you employ lanterns with more modes and fibers with more modes, then you can go even higher. And of course, it's something that we actually got feedback in our work from reviewers, and it's something we're also looking into, which is to perform a full QKD session with decoy states and a rigorous security analysis. And the other is, of course, to increase the transmission distance by employing longer fibers. And the main limitation here right now is really to, I mean, to go to kilometers, at least as from an experimental point of view, to be able to try, is the difficulty in acquiring these fibers, because they are not, the cost is considerably higher than single mode fibers. So it's not, and the distances that we have been using are very comparable to what other groups exploring the propagation of spatial states using this type of fibers, I mean, what they have been acquiring. So we are roughly in the same, at least in the same order of magnitude, roughly. But still it's, or at least one group has done a 10-kilometer experiment with a multi-core fiber. But yeah, but it's still roughly, we're not that far ahead. So it's not comparable to the experiments that have been recently done in MDI and twin field QKD that reach hundreds of kilometers. So we can't really compare those. And finally, so conclusions, one important consequence of our work in our view, which I didn't really go into because it's not quite the main topic of this conference, but this is a new way to generate and measure OAM modes fully in fibers. The traditional way has been to always use bulk components to prepare and detect the OAM modes, such as spatial light modulators and vortex plates. So we think our setup gives an interesting alternative, allowing maybe simpler integration and more robust setups for the future. So that's one interesting aspect. And the other is that we are also demonstrating that few mode fibers and photonic lanterns, they can also be an experimental platform for quantum communication and information, because they are able to coherently excite modal superpositions. So you can easily convert from a path state onto a state that's suitable for fiber transmission over longer distances. So for example, this could be the output of a integrated photonics chip connected through a lantern through all the way to transmit to another chip, for example. And we also showed little degradation in the transmission of the required states after 500 meters. So it also shows the potential of this platform for quantum communication. So it's definitely worth looking into going over longer distances. Well, I think that's it. Thank you very much for watching. Feel free to contact me if you have comments, suggestions, or questions. So the work, I mean, most of the work was actually done by Alvaro and Joakim, who are my PhD students here at Linköping. And this has also been a collaboration with Gustavo Lima from the Concepcion group in Chile. And I should also point out that Alvaro will be the one doing the live presentation on the last day of the conference as well. And yeah, okay, that's it from me. So once again, thank you very much.